answer. Okay. Do you have any question or anything? No, good. Okay, we will continue with the calculus review, some review on calculus. First, start with the linearization or linear approximation. Linear approximation. With one variable example, first of all. For example, f of x equal to sine 3x, and you know that this result only core about the x value near pi over 3, and which I want to show you the Taylor series. Another student joined the class. Okay, Taylor series of f centered at pi over 3. Let's see how it's looking. Do you remember the Taylor series? F of x equal to f pi over 3 plus f prime pi over 3 1 factorial x minus pi over 3 plus f double prime pi over 3 over 2 factorial x minus pi over 3 power 2 plus so on. Okay, if I write the f of x, f prime x, or f double prime x, we can see f of x is equal sine 3x. F prime of the x is equal 3 cosine 3 of x. F double prime of the x is equal to minus 9 sine 3x. F 3x is equal to minus 27 cosine 3x. And if I put here f pi over 3, it would be equal sine 3 times pi over 3. Sine pi is 0. If I put f prime pi over 3, it would be equal 3 cosine 3 times pi over 3 would be minus 3. And f double prime pi over 3 would be minus 9 sine 3 times pi over 3, again 0. And if double 3 times prime pi over 3 minus 27 cosine 3 times pi over 3 would be 27. And again, if I use for the fourth prime, fourth derivation would be 0. You know, it means that 0, 2, 4, 6, every odd derivative you have a 0 for this answer. And I can write here sine 3x would be equal 0 minus 3x minus pi 3, again plus 0 plus 27 over 3 factorial x minus pi 3 over 3, and so. And I can write here degree or Taylor polynomial is equal to linearization of sine 3x near pi over 3, and this is the linearization for the one variable, and I can write the degree I can write here sine 3x minus 3x minus pi over 3 equal pi minus 3x, and you can see the degree to Taylor polynomial, and the degree here is the degree of polynomial of the sine x is linearization of sine x near pi over 3. And if I use for function of two variable, for function of two variables, I mean fx and y, and you notice at this part Taylor series has a center at x0 y0. Has a Taylor series centered at x0 y0. It means that the f of xy would be equal to f x0 y0 plus fx x0 y0 x minus x0 plus fy x0 y0 y minus y0. You had this one before, and also you can add this one with the Taylor series. It would be the fxx over 2 factorials x0 y0 x minus x0 power 2 plus 2 over 2 factorial fxy, I write here x0 y0 x minus x0 y minus y0, and plus fyy fxx and so on. And if I write an example here, a quick example we will do here, f of xy equal x sine y, and x0 y0, the center is 1 and 0. Okay, it means that the linearization is linearization to f near 1 and 0. Let's start from the, you know that the fxy is equal to fx0 y0 plus f of x x0 y0 x minus x0 plus f of y x0 y0 y minus y0. It means that the f of x would be round after x sine y would be equal sine y, and f of x in 0 would be 0. F y round after y x sine y would be x cosine y. Then fy at center 1 and 0 would be 1. It means that the f of x and y would be equal. If put the x1 y0, you have a sine y sine 0 0, you have a 0 plus 1 y minus 0 is y, and it means that this, when you want to linearization, the center of the 1 and 0 fxy would be y. Okay, let's see other things that we can do with you today. Okay, critical points of a function of the two variables. Let's see how we can find the critical points. Critical points of a function of two variables as given f, x, and y in a point x0, y0 is a critical point if you remember what's happened of f, if fx x naught y naught or fy x naught y naught doesn't exist, does not exist, and also fx x naught y naught equal fy x naught y naught equal 0. For example, f x and y equal x sine y. We want to find the critical point. You know that the f of x is equal sine y and f of y equal x cosine y. we put both of them equal 0. It means y should be n pi. N pi is means that, for example, 1 pi, 2 pi, in any periodic pi, you have a 0y and would be n because belong to z, and also x would be 0 or y would be equal n plus 1 over 2 pi. The cosine pi would be 0, and you can see these 2 points are the critical points. It means that when x is 0, for example, 0 and pi, 0 and 2 pi, 0 and 3 pi, and so on, you have a critical point. If you want to classify the critical point, you should use the second derivative test. It means that to classify critical points, you should use second derivative test that you had before. Its delta is equal to fxx x naught y naught fy y x naught y naught minus fxy x naught y naught power 2. It means that here for this point delta less than 0 is saddle point. This one here delta more than 0. Now if fxx would be more than 0, you have a local minimum, and fxx less than 0 in local maximum. And for if delta equals 0, for this point we don't know, it's very inclusive point. We don't know this is what's happened at this point. For this example, f x y x sine y, let's see what is the critical point. Looking, I use the fxx would be root of the x, f of x is root of the x, and f of x was sine y. Then we put this one equal 0. Then fyy would be equal root of the y. Fy root of the y, and fy would be x cosine y. Then I put this one equal 0 as well. And now let's first of all do the derivative between minus x sine y, and that one already 0. And xy would be root of the y. F of x would be equal root of the y sine y. It would be equal minus cosine y. Now I back here use this equation equal to 0 times minus x naught sine y naught minus cosine y naught power 2. Now this one is 0, and from this one, if goes to the 0, it means that the you don't have any inclusive point. But as you look at here, this one is 0. It means that at every critical point, cosine pi, you should have this point, and this point is the saddle point, because this one is less than 0, and you have all our critical points are saddle point. If I plot this one, let me plot this one. X sine y, plot it. Come on. X sine y. Okay, tablet doesn't make it look good. But if I show you something in the graph, you have a 3D like this, and this, and this, and this. All point that you find it are saddle point. It means all of our critical point are saddle point. Okay, let's see what can we do next. One more example on chain rule, and then we'll finish the calculus review of calculus, and then we will continue with the differentiation of the equation. Application of chain rule. F, X, and Y equal to arc tangent Y over X. Okay, for the chain rule, I take U as a Y over X, Y X minus 1, and F of U would be equal to arc tangent U. And you know that the df over du for the arc tangent would be 1 equal 1 plus u2 from math 1110. You know that one. Okay, from here. Now f of x is equal to df over du. Do you remember the chain rule? If you have f here, you have a u here, then x, then y, dfu du over dx would be equal to 1 over 1 plus u2 and du over ds minus 1 u x minus 2. It would be equal 1. 1 now is u is y over x power 2 times minus y over x2, and you have here times these two together, minus 1 x2 plus y2 from f of x, and from f of y you have a df du dot du dy would be equal 1 over u2 plus round of the u y over x, and this would be equal 1 over 1 plus y over x power 2 times 1 over x, and times together at the end you have a x x2 plus y2. And this is the chain rule that you had this one before. Okay, I think it's enough some video. Let's back to the main part. Differential equation. Okay. Okay. Now, what is a differential equation? It is an equation for which the unknown solution is not a number but a function. You don't have any number for solution, you have a function that you should solve this function. For example, d2 ft over dt2 plus 4 ft equals 0. Look at here. You don't have any number, you just have a function, and it means we must solve for ft. It is the differential equation. Okay, let's do some real example. For example, like COVID is a pandemic, and when some pandemic happen, some scientists come to solve the equation. For example, after 2 days, 4 days, or 1 year, how many sick people we have, and how we can, control this problem. Okay, let's start with real world problem. Okay, for example, the start of a pandemic. The start of an epidemic. It means one new disease appear, and for example is The first time is 0 times 5 people is sick, for example. A new disease has appeared at time t equals 0. 5 people are sick. If I put IT as a number of infected people, number of infected people at time t, some epidemiology check the rate of the increase. The rate at which IT increases is proportional to IT number of the infected people to the IT itself. Okay. I can write here di over dt equal KIT, number of the people of the infection, and the K is constant number, and we use first order ordinary differential equation, ordinary differential equation. First order means the only first derivative of di over dt appears. Only first derivative di over dt appears, and ordinary means no partial derivatives, no partial derivatives. To solve this differential equation, we must find the IT, yes? It means that to solve this differential equation, we must find the function IT, and by inspection, the epidemiologist find the IT equal e power kt seems to work. It now means di over dt would be equal d over dt EKT, and would be KEKT, and would be equal KIT. Look at here, it's work. This one is exactly same, but this one means this function work for this epidemic. Okay, and you know that at the 0 time you have 5 people sick. Okay, and for this time, 5 people are infected at the start. It means I0 is 5. 5 equal to I0. And if I put a constant number, EK0 is equal A, and I know IT would be 5EKT, but we should find K as well. And also the epidemiologist told us by day 3, 8 people are sick or are infected. Now means I3 is 8. It means 8 equal to I3 is equal to A is 5, EK dot 3. And it means that the 8 over 5 is E3K, and 3K is equal ln 8 over 5, and it means K is equal 1 over 3 ln 8 over 5, approximately equal 1.6. Now we find the all variables. Now we can see, for example, after 14 days, 180 days, how many people would be sick. For example, after 1 week, I7, you have a 5, E.16 times 7 would be equal about 15 people. I21 after 3 weeks would be equal 5 E.17 times 21 is about 145. And for example, after 6 months would be 180. 5 E.17 180 is about 130 billion people. You know how increase the gradually because the exponential growth very fast. And some epidemic like this exponential function growth very fast. Now look at the equation from the first part that I see. df2 over, I told you the first page here, d2ft over dt 4ft, d2 d d2 ft over dt2 plus 4 ft equal 0. Okay. Now we want to see the differential equation here. You know that the second derivative of d, this one, is equal minus 4ft. If I take ft equal sine 2t, you know, I should choose something that shows oscillating motion, you know. It should be something ft that show oscillating motion, like for example wave, sound, light. And if I check here d2 sine 2t over dt would be equal to d over dt. The first derivative is 2 cosine 2t, and the second derivative would be minus 4 sine 2t. Look at here, sine 2t, if this sine 2t is look like this equation, work for this example. And in general, I can write ft as a sine 2t plus b cosine 2t. Both of them have an oscillating motion, and a and b, two free parameters. Okay, this is the family of solution. Okay, and if I write here, let's see, write for you here, this is a two parameter family of solutions. Now I want to write an initial value problem, IVP. What's that? An initial value problem, IVP, is a differential equation differential equation together with enough initial data to find a unique solution. Find a unique solution. For example, di by dt is equal to 1.16 it. And the first solution for that example, in first time 5 people 6. It means this one. Initial value, and this one is the differentiate equation. Or another example, d2ft over dt2 plus 4ft equals 0. And you find two solutions. You find if you put f0 2 or f prime 0 minus 3. Again, these two now are initial values. You should find the initial value, initially to find the unique solution for the IVP, initial value problem for the IVP. And what can we say about the solution of, what can we say about the solution of dy over dx f of x and y. Okay. For example, I can write dy over dx equal x minus 1. First of all, we should draw a direction field. We should draw a direction field. Let's see how we can draw a direction field. If you have x here and y. Now look at here. If I put x0, y0, this slope is 0. Yes, in x0, y0, this point. Let me make a table here, or make a table here. X, y, and dy over dx, that's a slope. Yes. If put x0, y0, the slope is 0. Would be like this. If put x1, y0, the slope is 1. x1, y0, the slope is 1. If put x2, y0, the slope is 2. It's more like this. It's like this. If put 1 and 1, again, slope is 0. 1 and 1, slope is 0. If I put minus 1 and 0, the slope is minus 1. It look like this. And this point, the slope is the minus 1 and 0 is minus 1. Is 2 as 0 minus 2. Here is 1 minus 1 plus minus 1, and it would be minus 1 minus 2, and 2 and 2 slope again is 0. This point 1 and 1 is the one typical shape of the direction field, and I can show the graph like this. Is equal yx. This is the direction field of x minus 1, and the graph, if you plot this one by computer, show you the better graph, and the graph of the function, yx pass through the tangent which passes through the point, this point. If show you by computer, pass through -2 and 0.5, and is the tangent to all the, and is a tangent to all of the slopes. Okay. The other method that you have in a differential equation is the Euler's method. Euler's method. Was that this method? And iterative algorithm for computing and approximation solution to first order IVP, for example. And if I write here dy over dx is equal to fxy, and yx0 is equal y0, pick, first of all, we should pick a step size k or h, and then start at x0, y0. For example, this point is x0, y0. Then the point x1, y1, we can here a step size h. This point x0 plus h. It means that the x1 is equal x0 plus h, and y1 is equal y0 plus f of x0, y0, h. And we can repeat this one for the another point, for point x2. It means that the repeat is x2 is equal x1 plus h, and y2 is equal y1 plus f x1 y1 times h, and you can keep going this one to the end point. Xn plus 1 is equal xn plus h, and yn plus 1 is equal yn plus f xn yn times h. This is the Euler's method. Let's give you one example on this, and let's see how it's looking. One example, dy over dx equal y minus x, and y minus 2 is 0.5. And let's see how we can choose h. As you can see here, y minus 2 is 0.5. We choose h equal 0.5, and for the step 1, if put x0 minus 2, it means y0 0.5, it means y x0, show you y0, and it's, you have this one, you have an equation f x y equal x minus y. Now x1 is equal to minus 2 plus h is 1.5, and y1 is equal y0 plus f xy and x0 y0 times h. That means y1 is equal 0.5 plus minus 2, use this equation, minus 2 minus 0.5 times 0.5 would be equal minus 0.75. First step. And we should check how many steps we need to find okay, how many steps we need to find y0. We want to find y0. Okay, let's see how many steps we need. Next step, x2 is equal x1 plus, it should be minus, plus h, and y2 is y1 plus f x1 and y1 times h. It would be y2 is equal 175. Use the equation times h, and y2 would be equal minus 1.125. Okay, I still need to keep going. Let's check x3. Is x2 plus h, and y3 is y2 plus f, x2 y2 h would be equal about minus 1, 0, 6 to 5. Okay, let's keep going. Let's see. x4 is equal to x3 plus h. Now is 0. Yes, we found it. y4 is equal to y3 plus f x3 y3 dot h would be equal minus 1.0625 plus minus 0.5 minus 10625 minus 10.5 would be equals minus 0.78125. We use the Euler's method, and if I use the IVP plot, you can see your graph should be like this. Okay. Okay. Now back here, I will show you. You have a question here. Look at here. dy over dx is the tangent or a slope. Yes. When I put, let me copy this one. I will back here. Let me finish this one and I will explain for you later. Let me finish this one. And if your plot would be something like this, that you point to find it is x0, y0, then you find the x1, y1, then you find the x2, 1, 2. This point is x4, y4. That x is 0. And if you continue that point, you find the shape of the graph. Each point show you x1, y1, you have an x2, y2, x3, y3. If you put in the graph, at the end you have a plot. Okay. Now back here, I will explain for you. dy over dx is equal to x minus 1. X minus 1. Okay. I put x, I put y, and I put dy over dx, that is the slope. If I put x 0, y 0, the slope is 0. If I put x 1, y 0, the slope is 1. If I put 2 and 0, the slope is 2. If I put a slope If I put -1 and 0, slope is -1, -2 and 0, slope is -2, and so on. For example, 2 and 2 is 0. Now how the slope is negative or positive. Okay. Now look at the graph. I want to show you here. If you have these 2 points in the graph, or better, these 2 points, I want to show you how the negative is look like this and positive look like this. Let's see how it's looking. Its point is 1 and its point is 2 and 2. I want to find the slope of this graph. Is y minus y1 x minus x1. Okay, it would be equal to, or write y2 next. What is the y2 is 2. What is the y1 is 1. What is the x2? 2, x1 is equal. You know, the slope is positive. The shape is look like this. Now, if I choose these 2 points, again, -1, -2. Now, y2 minus y1 over x2 minus x1. y2 is 2 minus y1, 1, -2 minus -1 is 1 over -1 is -1. The slope is negative, positive. It means that here, when the slope positive, you have such a this at that point. When a slope is negative, it's like this. But when it's -2, for example, this point, I increase this one. 2, 3, 4, 5. You can see I want to check now a slope after this line. Or let me show you for -2. Smaller than this. This point. For this point, y2 is 3, y1 is 1, x2 minus is equal -2. You know, when the number is bigger, if a first slope is look like this, a second slope is would be this. The more you have it, more tint here, you know, extended. And for this one is look like, for example, -2, the slope would be like this, or 2, the slope would be more like this. And when the 0 is a slope, you don't have any slope. Is it clear now, flipping? Okay, good. And if you put this one in the contour plot, or IVP plot, all points show you like this, the shape of how the graph goes. like here. If I continue this one, show you the shape of the graph is going, all the line would be such a this. In the contour plot, if you put this one, the IVP plot. And you can use this one by computer, is very easy, but with hand you can choose point by point. But in the Euler method, as I told you, in the Euler's method, you can pick some H, but be careful. Don't pick a very big H because give you the wrong number. You should choose the fine H. May depend after your calculation. And when you find that one, you can find x1, y1, y1, x2, 1, 2, and repeat at this point that, for example, this point as you pass through the x-axis. If you pass it through x-axis, you should continue this one to find the y0. If you ask to pass through the y-axis, it means you should keep going till x would be 0, This point pass through the y-axis. It means x equals 0. And this point, if you keep going to find the point, you will find the point. This point is pass through the x-axis. It means y equals 0. And when you add those points together, you can plot the graph. This is the Euler's method. Okay. This is the differential equation. One is not, it wasn't a big deal. Next week, we will continue differential equation 2 and 3. Do you have any questions? Okay. Okay, good. See you guys. Have a lovely weekend, and I will see you next week. Bye-bye.